We will not go into details of many beautiful codes that people proposed, except maybe this one, the 7-qubit code. I would like to take a moment to discuss the 7-qubit code, simply because it's an excuse for me to show you something that is called the transversal constructions of quantum logic gate on encoded qubits. So when someone comes to you and say, well, I have this wonderful stabilizer code. So you say, well, show me the stabilizer. So here are the 6 stabilizer for the 7-qubit code. So 6 generators for the stabilizer group. So they partition this 2 to the 7th, right? So it's 128 dimensional Hilbert space into 64 two-dimensional subspaces. And as you can see, each stabilizer here involves either 4 X operator or 4 Z operators. Moreover, you can see that if you look at these 3 operators here, they are just exactly like this one, except that you swap X to Z. The first thing you can do is to ask, okay, what kind of errors does this code correct? And then you can convince yourself that all single qubit errors on any of the 7-qubit will lead into different error syndrome. And there are many other errors that will lead to different error syndromes, but at least this code will correct for any single qubit error. So we say that this code allows us to encode 1 qubit into 7 qubits. So we have 1 logical qubit, which is represented by 7 physical qubits, and that can correct for a single qubit error on any of those qubits, of course. Now then you look at the normalizer. So you look at first all possible operators that commute with the stabilizer, and you know that the normalizer in the Pauli group will give you the logical X and logical Z. So the logical X in this particular case has a nice form. It's just n-fold tensor product of X's on each qubit, and the logical Z likewise is n-fold tensor product of Z's. So we have 7 Z's and 7 X for logical X and logical Z. Now, what about the normalizer, but not within the Pauli group? But we just go towards the unitaries, and then we look at the Clifford operations. And again, you can easily convince yourself that the Hadamard can be then nicely implemented on the encoded qubit by applying the Hadamard gate to every single qubit. And if you take our phase gate, S, just don't be confused, sometimes I use S for the elements of the stabilizer, but we are going to the gate notation here. So S is our phase gate, the gate that is described by the matrix, which has 1 and I on the diagonal here. So the S gate likewise can be nicely implemented by applying, in this case, S dagger to every single qubit. So it is 7-fold tensor product of S dagger here. So that's actually very nice. You can even go further and just look at the implementation of the control knot, and you realize it can be nicely implemented on the encoded qubits by simply applying control knot pairwise to qubits. So for example, if you have a circuit like this, which is simple Hadamard and followed by a control knot. So you have 2 qubits here. The first one undergoes the Hadamard and then serves as the control for the control knot gate, and the second qubit just serves as a target for the control knot gate. Now suppose you want to encode this qubit and this qubit into 7 physical qubits. So you have then a manifold of the 7 qubits for the first qubit here, and another manifold of 7 qubits. So it's a code block of 7 qubits and another code block of 7 qubits. So now we want to implement both the Hadamard and control knot on the encoded qubits. So we do it in such a way that we don't leave the code space, really. So in this case, we just apply, using this rule here, we apply the Hadamard gate to every single qubit in the first code block. And then the control node is just implemented pairwise. As you can see, I just take the first qubit from each code block and apply the control node, and just go to the second, and so on and so forth. So this kind of way of implementing quantum logic gates is called transversal. It's very nice because first of all, it's simple, right? So it's a nice pattern. You can see right away how to do it. But the important thing about this kind of construction is that if error happens, the transversal construction allows us to confine errors. It doesn't sort of like propagate errors to different code blocks. So for example, if error happens somewhere here on this qubit, it will be just confined to this qubit after the Hadamard gate. If it comes to the control node actually may copy the error to the second block. But it will never happen that one error will generate more than just one error per block, right? So one error in this block will be confined either to this block, at most will affect through the control node gate one of the qubits in the second block. So that will be important, because if we do sort of error correction and we have codes that correct for, say, one error, then we can actually maintain through transversal constructions plus frequent error correcting codes or error recovery, we can actually maintain those this kind of network, this kind of circuit clean of errors. So that's very nice, except there is one thing that may worry you a little bit, is that we actually cover the transversal constructions for a certain class of gates. So we talk about X and Z, logical X and Z. In fact, we went to the Clifford group, so we talk about implementing the Hadamard and the S gate and the control node gate in the transversal way, so that we cover the Clifford group, right? But we do know that the Clifford group is not universal, so the set of gates from the Clifford group is not universal. We talk about that. Now, in order to make it universal, you have to go outside the Clifford group, and in this case you may want to add the famous T gate, right? So which is 1 e2i pi by 4 on the diagonal. Now, unfortunately, we don't know how to implement the T gate in the transversal way. So it's a little bit of an art to implement it. There's people are trying this way and that way. There are different approaches how to do it, but there's no transversal constructions, unfortunately, for the T gate. That is true as far as the 7-qubit code is concerned. It's code related. There are some other codes where, for example, we do know how to implement T gate in a transversal way, but then we have problems, say, with the Hadamard gate, which we cannot implement the transversal way. So it is a little bit like, sleeping under a small blanket. You try to sort of cover yourself with a transversal construction blanket, so you cover some of the gates, and then you leave some other gates exposed, and they don't have a transversal construction. So so it's certainly the code dependent, and the bad thing is that we know that no matter which code we use, we cannot find nice transversal constructions for the whole class of universal gate. So that means that we have to work harder. That requires a little bit of creativity, how to implement gates in a non-transversal way. But that's part of the fun. Life would be probably too easy if we could implement all the all sets of universal gates or set of universal gates in such a nice and transversal way. So the transversal constructions are very important for the whole concept of fault-tolerant computation. So let me now just mention briefly how fault-tolerant computation works, and we will conclude with something that is called the threshold theorem.